Hey guys, we've got section 5.2, the first day of it. We're continuing to evaluate limits analytically, which means analyzing the limits. We have a lot of different strategies to do that. This very first one's kind of like a warm-up. What we have here is a basic parabola equation. Looks like it's shifted right one and down one. And then I've got these three different limits that I need to analyze. And so remember, just they wrote f of x here because that's what this equation was, or this function was defined as. It could be g of x or h of x or anything else, so don't let that part freak you out. But then remember that the x value down here, that tells you what the x value is approaching, and if there's not a plus or minus, you have to look at both sides. So in this case, let's use our shortcut. So since this is a basic parabola, it's not a piece of a parabola, it's the entire parabola with arrows that goes up forever, and it gets wider and wider and wider. That's what defined everywhere on the whole domain of x means. Technically, it just means that it's not like undefined somewhere. So keep that in mind. I'll get more into that in just a second. But if I take the 0 and I just plug it into the formula, what do I get? I get 2, 0 minus 1 squared minus 1. Let's remember order of operations here. This means negative 1 squared, and then you times by 2. There's remember order of operations. You do exponents before you multiply. So wanted to point that out. So negative 1 squared is 1, times 2 is 2, minus 1 is 1. Excellent. Let's take the negative 3 and just plug it in. And remember, the reason why I'm allowed to just plug in these numbers here is because this parabola is the entire parabola. It's the only part of the graph. It goes forever. It's defined everywhere. It's not like a piecewise function where we have different chunks of different graphs. So anyways, when I plug in negative 3, I get 2, negative 3 minus 1 squared, minus 1. So negative 4 squared becomes 16. Times 2 is 32, so getting kind of big numbers. That's okay, minus 1 is 31. Okay, and then last one, I'm going to plug in, what is that, 4? So I get 2, 4 minus 1 squared minus 1. 4 minus 1 is 3, squared is 9, times 2 is 18, minus 1 is 17. So there you go. Let's just get a really quick sketch of what this parabola actually looks like, just because remember how graphing sometimes can help, although it's not always necessary. So remember that we decided that the parabola was shifted to the right one and down one. So what I'm going to do is put a little tick mark, right one, down one. This is the vertex of my parabola right here. I also know that it points up because that 2 is positive. And then if you remember anything from Algebra 2 about that 2 value, that means you go up 2 and left 1 and up 2 and right 1. So that 2 in front of the parabola actually makes it a little bit more skinny than a regular, I guess, quote-unquote normal looking parabola. Anyway, so here is what our parabola looks like. This is just a rough sketch. You can get a lot more points if you needed. Anyways, but let's actually look at the graph while trying to analyze these limits. So the first one was as x approaches 0. So here's x equals 0, it's the y-axis. So my left hand and my right hand are both approaching this y value, and they're going to meet right here at a y value of 1. And that's exactly what we got when we just plugged in the value. Okay, so if we wanted to look at the other one, which was negative 3, so negative 3 is like way up here. Because negative 3 is over here on the x-axis, which means for my parabola it's going to be like way up here. But my left hand and my right hand are both going to meet at whatever that y value is. And how do you figure out what the y value is? You just plug it into the equation. So they're both going to meet at the same place, and they meet at the y value of 31. Same thing with x equals 4. So again, this parabola keeps getting wider and wider and wider, but x equals 4 is out here, which means the parabola is going to be way up here, and my left hand and my right hand are both going to meet at that y value. How do you figure out what the y value is? You plug it into the equation. Anyway, so moving on to number 2, this was find the following limits without graphing, because you don't have to be concerned with what this graph looks like yet. We will get to that a little bit later in the chapter, but I'm going to try and do the shortcut by just taking this 1 and plugging it into my equation here to figure out what the limit is. So I plug in 1 to the numerator, I can solve that, but what happens when you plug in 1 right here? You get 0 in the denominator, so that is bad. You cannot plug in 1 to the denominator because it's undefined. So let's think back to a little bit of Algebra 2. We're kind of stuck right now. That means I can't use 1 in this equation, so the equation is not, or the function is not defined over every single value of x. There is a value that I'm not allowed to plug in, and that happens to be 1, because that makes the denominator equal to 0. So let's think back to Algebra 2. Do you recognize the numerator as being able to be factored? We will get more into this later on in the chapter, but here's an intro. Yes, the top factor is what multiplies to positive 1 but adds up to negative 2. I believe those are both negative 1. So this is weird. Do you remember this from Algebra 2? Something factors and cancels. This means that you have a hole in the graph at x equals 1. How did I get x equals 1? Whatever you canceled, equal it to 0, and that gives you the x value where the hole is. When you cancel something, that means you have a hole. And while we're talking about holes, we should be a little bit more calculus savvy. These are referred to as point of, do you know it? Discontinuities. AKA hole. But you guys are trying to learn a little bit of calculus here. These are prerequisites. This is stuff you're going to get big time into when you get to calculus next year. So we call this a point of discontinuity at x equals 1. There happens to be a hole there. So what does this graph actually look like? So see what's left over? I was able to cancel the x minus 1s. So my entire equation, f of x, is just x minus 1, because the other two x minus 1s canceled. So do you know what y equals x minus 1 actually looks like? Isn't it just a line like y equals mx plus b, starting at negative 1, and the slope is up 1 over 1, up 1 over 1, whatever? Here's what that graph looks like, except at x equals 1, there is a hole. So that should be an open circle right here. There's a hole in the graph, otherwise it's just a regular linear function. So let's see if the graph now is actually able to help me figure out the limit as x approaches 1. So left hand, right hand. What are both of those hands getting really close to? What's the y value there? 0. Okay, and so to be able to do this without graphing, remember here's what our function is after we simplified it. And so that means that f of x is just this x minus 1 thing. So when I do the limit as x approaches 1 of f of x, when I plug in the 1 to the new and improved simplified version of the equation, what do you get? 1 minus 1 equals 0. So we didn't have to have the graph, but I wanted to explain through that problem. Here's what the graph looks like. Here's what's happening. Remember that there's a hole. Remember that's called a point of discontinuity. We are still allowed to do our plugging in this number. The problem was this function simplified. It was like a fraction that wasn't reduced. So after you reduce it, you have a function that looks a little bit different. Now you're allowed to plug in the 1 right here, and that's how we get 0. Looking at the graph, that also makes sense. My left hand and my right hand are approaching a y value of 0. Let's look at number 3. In this case, I'm going to plug in the 5 and see what happens. Ooh, tan, this is weird. Okay, so when I plug in the 5 to evaluate the limit, let's see, tangent 5 pi over 4. If you think back to unit circle, that is third quadrant. Oh my gosh, yes, there's some unit circle stuff in calculus. What is the tangent there? Oh, it's just 1. Aren't the, at 5 pi over 4, remember that's a 45-degree reference angle, and this are the same, so the y and the x are the same, and they're both negative in quadrant 3, which is why it cancels out to be a positive. There's a little bit of unit circle blast from the past. Okay, let's take the 0 and plug it in. There's no x. Okay, so now what do? Well, do you know what the function 8 looks like? So just remember, that's a horizontal line. There's no x to plug into. That's because no matter what x is, the y value is always 8. So when you plug in 0 to nothing, the answer is always 8. When you plug in 1, the answer is 8. When you plug in 17, the answer is 8. So no matter what, this limit is 8. You can think about it in terms of the graph also. What happens as x is approaching 0? What is my left hand getting close to, and what is my right hand getting close to as I approach 0? The y value right here is 8. My hands are going to meet at a y value of 8 when I approach 0 from the left and the right. Okay, same thing with this other one. What about -4? As x approaches -4. Okay, cool. Where's -4? It's right here. Okay, so my left hand, my right hand, what y value are they going to meet at? Right here. Y value is still 8. No matter what the x value is in a constant function, which is a horizontal line, they always meet at that y value, which is 8. How about number 5? I'm going to take my 0 and plug it in for the x. So I get natural log cosine 0. Okay. What is cosine of 0? Oh boy. What is the x value at 0? X value is 1. And just keep that natural log. I've been ignoring it so far, but I do know how to simplify cosine of 0. It's 1. Just drop this natural log down. Do you know anything about natural logs and logs? You could type this into your calculator. Find the ln button. When you hit 1, what is it? Remember, logs are a way of asking you what's the exponent. In this case, the base of a natural log is e. So e to what power gives you 1? Anything to the 0 power is 1. So any log of 1 or natural log of 1, the answer is always 0. A lot of algebra 2 coming back at you guys. Okay, piecewise function. I don't really want to graph this. And especially because the directions told me not to graph it. So let's see what happens. As x approaches 2, oh, we've got this little minus sign here. Remember, that means from the left. So can you tell me, see how we've broken up this piecewise function into numbers less than or equal to 2 and numbers greater than 2? Can you tell me where 2 from the left fits in this piecewise function? 2 from the left means I'm using x values of 1, 0, -1. Those are all to the left of 2. This means to the left of 2. So when you're looking at a one-sided limit, only approaching from one side, which in this case from the left side, you only find where it fits into in that piecewise function right here. So this means x from the left. Therefore, plug in this 2 to only this part. We're ignoring the x greater than 2 because that is not what this limit is restricting us to. So when I plug in 2 from the left, I'm taking the 2 and I'm plugging it in right there. -3 times 2 plus 1, that's -5. What about when I do 2 from the right? So you see how 2 from the right actually fits into this category of the piecewise function? That means 3, 4, 5, 6, we're approaching from the right, anything on the right-hand side of 2. So I'm plugging in the 2 to the x minus 6. Okay, interesting. So what is the limit as x approaches 2 from either side? I got -5 from the left, or from the left, and I got -4 from the right. Are my hands meeting? One of my hands is at -5, the other hand is at -4. That means the limit does not exist. So here is how you are to do a piecewise function without having to graph it. You could graph it. You guys know how to graph this. This is a linear function stopping at at 2 and only using the left-hand side. This is also a linear function starting at 2 and using the right-hand side. My two hands are at different places. One of them is at -5, the other one's at -4. This is how you do limits by plugging them into an equation without having to look at a graph. And that's what we wrote in the last video. You remember how you wrote those bullet points? How to evaluate a limit looking at a table, how to evaluate it looking at a graph. This is how to evaluate it looking at an equation. Those are some of the notes that you wrote down. You like plug something into one side of the equation, plug something into the other side. This is what I mean by the sides. Here's one piece of the function and here's another piece. And you just have to look at the 2 from the left that fits into this category. So I'm using this function. 2 from the right fits into this category. That's why I'm using this function. And if those two numbers are different, that means that the limit does not exist. If these two numbers are the same, that means that that is the answer to the limit. Okay, so besides that, I'm going to skip these two examples. You guys don't need to worry about those. I do have just a couple notes for you to fill out that might help as we're progressing through these limits. So note number 1, try plugging in the x value from the limit if you can. And so the reason why we say if you can is because in example 2, when I tried to plug in that x value of, I believe it was 1, it made the denominator equal to 0. Therefore, I had to use some algebra 2 skills in order to manipulate that equation and try something else. After I simplified that equation, I was able to just plug in the x value to what was left over of the equation. Always check the left and the right to make sure it's the same value approach. That's exactly this last example that we went through. So we were asked to evaluate the limit, but 2 from the left was one equation and 2 from the right was a different equation, and those were different numbers, which is why it did not exist. Sometimes they'll be the same number, and in that case, if they're the same number, that is your answer to the limit. That's what I'm talking about in number 2. And then number 3, just remember, if you get confused or lost or if you freak out about something, you can always do a sketch of the graph, because that's the first way that we started talking about limits. And it definitely helps to have a visual, and imagine tracing the graph with your hands and seeing if they're going to meet or seeing if they end up in different places. That can be helpful, but sometimes it takes a little bit of time, so you always have that to fall back on. That concludes the notes for the day, you guys. Thanks for watching. I hope you have a great rest of your